Today we'll start by proving it. Every surface link in S4 emits a BC bridge trisection for some values B in natural numbers and C a triple of natural numbers. Let's just remember C is this triple C1, C2, C3. And just in case you've sort of forgotten exactly what this is talking about, a bridge trisection means we're going to decompose the surface into three pieces, each of which is a trivial disentangle, and such that the trivial disentangles intersect along trivial tangle with this sphere with marked points in the middle. So that's sort of the structure we need to arrange. So how do we go about doing this? Well, the first thing we do is we're going to put S in normal form. So isotope S to be in normal form with respect to this, I guess, this Morse function. On S4. And so that isotope is in normal form, so that it is the realizing surface S, say, LB. That's what we call it. L1 B of the banded link LB. L1. So I'm calling this bottom link L1, the link that's the boundary of the minimum. And then let's just set up some notation. We're going to let the cardinality of L1 be C1. We're going to let the cardinality of B equal N. And we're going to let the cardinality of L3 equal C3, where L3 will be the result of resolving the bands of B along the link L1. And this will be the conventions throughout the next day or two. Okay. Okay, so we just put the surface in normal form. Next, we're going to choose a bridge sphere inside this equatorial cross-section. And we just choose it so that it's a bridge sphere for this link L1. And after perturbing sigma, maybe I'll make a little asterisk here. We can assume that we have a banded bridge splitting. Remember, this is a decomposition into two trivial tangles glued along the bridge sphere so that the bands are level in the bridge sphere and framed by it. And we have this nice decomposition into tangles. It is a banded bridge splitting. Let's call it a banded B bridge splitting. Okay. So the asterisk is that when I say perturb sigma, I don't know if I've really harped on this before, but when we were sort of doing stabilizations, or when we were doing perturbations of bridge splittings, I think I mostly presented that as take your link and isotope your link so that it crashes through the bridge sphere some extra times, right? Maybe I'll just draw sort of like a picture here. So when we were talking about perturbation of bridge splittings, we were thinking of something like this, which is totally valid. And this is sort of suggestive that I've moved my link relative to the bridge sphere, but of course we could do the opposite, right? We could also move the bridge sphere. Let's see what that would look like. I think that would look like this. Yeah. Okay, and of course then we could sort of isotope the bridge sphere back to where it was and hold, this is an isotopy of the bridge sphere, leaving the link fixed, but then we could return it to its initial place with an ambient isotopy, and we get this sort of picture. So the point of this comment is just that there are sort of two views here. We could think about perturbing our surface link, so that we're sort of changing intersections with this central sphere, this bridge sphere, or we could just think about moving the sphere inside the S3 cross section, and that's the view I want to take here, because I'd like to keep this nice realizing surface form where we have the banded link and then vertical kind of turrets coming off above and below. And so if all I'm doing in here is moving this auxiliary sphere around, then I still have a nice vertical surface. I think I'd like to keep it that way. Okay. Okay, I actually finished a sentence. That's good. Yeah, so maybe I'll just draw a quick sketch so we can kind of have an idea of what's going on here. So this is if this is our equator right here, then we've some colors. We've sort of done this sort of thing. That's one side. And on this side, we see some of this. Something like that. So this is so this is meant to be sort of T2. This is meant to be T1. One of these is probably reflected. Let's not worry about that. And we also have bands. So let's make our bands orange. So the bands, and remember, we have this sort of convention of once we are in a banded bridge splitting, we sort of perturb our bands into the T2 half. Okay. We're not going to worry about orientations because I think I got backwards. Okay, so now what we want to do is, we know what this surface sort of looks like, right? We resolve the bands and we go up and cap off, and we go down without resolving the bands and we cap off. And we want to split this vertical thing into 3 pieces. So let me tell you what the 3 pieces are going to be. So our first 4-dimensional piece is going to be negative infinity to -1. So the portion of the force sphere lying at height -1, at most height -1. And the disk piece, the first disk piece, the first set of patches is going to be the intersection of our surface in normal form with that interval, which is just the portion below there. So let me maybe come over here. You'll have to bear with me while I draw some pictures, as usual. Okay, so, and I'm going to redraw this whole thing. So what do we see at time -1? Well, we see the same thing that I just drew there, except without the bands, because the bands don't live at time -1. Any questions while I'm drawing? Okay. So what do we have? Well, below this, we have our pair Z1, D1. Okay. And so we have that Z1, D1 is a trivial C1 disk tangle. And that's just because all it is the cups with a product of them. So that's our first piece. Similarly, we're going to let Z3 be the sort of upper part of our surface. Oh, sorry, this might be it's a little bit more complicated. That's right. It's going to be the upper part union part of the sort of middle area. So it's also going to be B1 pushed through the interval -1, 1. And D3 is going to similarly be, it's going to be our surface intersected with the upper part, union with the tangle T1 pushed through the interval 1, 1. Okay, so maybe I'll draw some more of a picture here. Starting at the bottom really throws me off. Okay. I think we'll have something at least resembling something useful. Okay, so.
So you mean cross, Meier? You have some notation, B1.
What did I write?
You're right, you said pushed through.
Yeah, I do have some, yeah, this is notation, that's correct.
Good notation.
Yeah, it's the notation that was introduced by Cauchy and Shibuya and Sloan. Yeah, I think it is good notation.
Flow it forward by the time.
You flow it, and it might not, you know, if it doesn't necessarily correspond with the intersection of the surface with that. That would be with the subscript. Okay. Yeah, that's right. That's good to remember. It's subtle notation, but once you know what it means, I think it's useful. Okay, so what are we talking about here? Well, we're talking about, so this is the interval -1 for the time -1, 1. So up here we have Z3, D3. Okay, it's this 3 ball, B1, times this length 2 interval, and then everything sitting above time 1, and then the disk is the intersection of the surface up here, which is just the cups, plus this piece of T1 cross I, which I won't draw. So since this is just the cups plus like half of a color neighborhood, we have that D3 is a trivial C3 disk tangle. Okay. So these are sort of the two pieces that are most obvious when you're in normal form. I mean, a normal form is almost like 2 trivial disk tangles stuck together. But one thing I guess I didn't really mention, so maybe we'll have an aside here, which is that the union of 2 trivial disk tangles along their boundary, but say they have the same boundary, is always a double, and in particular and an unlink of two spheres. Okay. And this is because they can sort of, this is a consequence of the result that any two trivial disentangles are isotopic bone boundary. So if you take two of them and you glue them together, you're always just doubling an object, which means you're just getting like the union of spheres that just look like this, right? So this philosophically says there's no hope in decomposing knotted surfaces into two trivial pieces like we did with knots. So I don't think I really made that explicit earlier, but that is why the proof is sort of going to get a little bit interesting right here. Okay, so what are our other pieces going to be? So we're going to let Z2 be the 3-ball B2 through the interval -1 to 1, and we're going to let D2 be the intersection of our surface link with that interval. Okay. So maybe I can draw in some more bits to the picture now. We got this sort of thing going on, and then in this level we have bands. And then I walked all the way over here to grab a piece of chocolate home. Then, of course, what happens after the bands is we resolve the tangle. So we get this, which is this tangle like that. And so we have this nice little piece. We have this nice 4-ball here. This 4-ball surface pair, Z2, D2. And so Z2 is clearly a 4-ball. And D2 is a trivial disk system by lemma 2 from last time, right? That's why I gave it a number, just for this moment. By lemma 2, D2 is a trivial, and it's a trivial B minus N disk tangle. Yeah, so actually let me write it like this. Let's write it as a C2 disk tangle with C2 equals B minus N. I could have added to my conventions over here, but C2 will work for both. Okay, cool. So this is good. We've cut and this is the entire surface, right? So we have everything below this level, this half of the middle level, and then this half of the middle level plus the top level, and it's a decomposition into 3 trivial disk systems, disk tangles. So now we need to check that these things meet along the right types of pieces. Okay. So this just boils down to examining these intersections. So let's leave this alone. And you could just by looking at that schematic over there, you can already see that. Well, you can probably see the entire punchline, but some of them are even particularly obvious. The intersections. All right, so let's just be explicit about it. First of all, let's consider Z1, D1 intersect Z2, D2. Which we'll denote by B2, T2. Well, and to disambiguate it with something that was called this earlier, what we're really doing is we're taking the copy of the second tangle that's living at time -1, because this is where Z1 intercepts that. And well, it's just B2, so it is a trivial B tangle. And similarly, Z2, D2 intersect Z3, D3. What is this? Well, let's call this D3. Oh, sorry. You know, the first case always lulls you into thinking you got it. But this is a little bit more interesting because we now have to take sigma x pushed through the interval -1, 1 and union it with the paired B3, T3 at time 1. Oh, and I think I did neglect to mention today, although I said it last time, maybe I'll write it over here. B3, T3 was our notation for B2 and then T2 with the bands resolved. And so that's what we're seeing right here. Just T2. 1, 2. All right, so this intersection is actually a little bit more interesting, so let's think about it for a second. Well, so this is, and let's go ahead now and just call this B3, T3. And this is a trivial B-tangle, but only because of the lemma we proved. I guess this was last time? No, I guess it was even longer ago. Just 2 classes. Which, what was this lemma? The lemma was that B3, T3 is a trivial tangle because we've attached these bands in banded bridge position. You guys remember that? Okay. There were two consequences of banded bridge position. One was that the result of attaching the bands to T2 was a trivial tangle, and the second was that the trace of the band attachment is a trivial tangle. Okay, and then, so lastly, Z3, D3 intersect Z1, D1. What is this? Well, this is just B1 at height -1. B1, T1 at height -1, which I guess we'll call B1, T1. And this was already a trivial B-tangle. And then lastly, let's let sigma x just define this to be, or we'll notice that the intersection Z1, D1, intersect Z2, D2, intersect Z3, D3, which we refer to as sigma x, is really just sigma x at time. Or is there a product here, or is this? I think it's just that time -1. It's this copy down here. So B1 is fine, B2 is fine. B3 is kind of funny, right? It's this like waterfall tangle. It comes down this side. And that establishes all the properties of a bridge trisection. So we have the right sort of decomposition of the surface. Okay. Great. Does anybody have any questions about that? Okay, now last time I did talk about triplane diagrams, right? So I probably gave the definition of a triplane diagram and a few examples. Okay, so then we probably can, so one nice thing about this proof is not only does it give you, not only a proof, but it's also constructive, right? It tells you how to start with a banded link and construct a bridge trisection. So this is a good skill, so let's example of construction of a bridge trisection. Okay. So the first part is to start with a banded link. L1B for your surface and asphalt. Okay, so now I can't remember which guys I've already put in banded bridge. Did I put the double of the stevedore disc in banded bridge position already, or did I do the like mixed gluing and the sponge shuffle? Trivia. Anyway, I guess I'm not going to change. I guess your answer is not going to change anything in my mind. So let's just carry on. Okay, so we have. I don't think I did this one. So that's an unknot. Let's add a second component to make it an unlink. That's this nice unlink. And let's see what bands will be orange and purple. So one of the bands which gives us back the stevedore knot is this guy. And I guess if we're going to take the double of this surface, then the next band we want is this sort of dual band to the orange guy. So this is our LB. And then, so step 2 is to put in banded V bridge position. Banded V bridge position. And then, yeah, just we're thinking of this as living in the equator. And just to keep the notation. And farm. Okay, so what does that step look like? On this example, let's draw our bridge. I won't do it in 2 steps like I did before. I'll just do it. Something that looks like this. Okay, and then the bottom half is a little bit simpler. This is the picture. All right, and so let me see. This orange band ought to go out here, and the purple band ought to go. It's different. Okay, well, let's be a little bit careful here. So if I pull that down like that, this maybe I think I did my bands differently than my notes, so I'm just going to do this one on its own. Okay, so I think I want this guy to come out here like this. And this guy to come. Let's try this. So the key technique for doing this sort of thing, for me, is to just guess what it should look like and then check whether it's right. So I think that's what the orange guy ought to look like. And
Purple would be just above and below that on the other side.
up here, right?
No. Well.
Oh, it would sort of be like right there, huh? Okay, but we don't quite like that. I see. And then I'm up got my 4 bridges already. So what there should be a crossing. Let's do it a little differently. See, I told you I could never do this. What if we go down?
Remind us what you're
Okay, I'm gonna
need. Yeah.
What?
Remind us what you really, it's,
What I'm doing?
what you really need. You need those bands to be horizontal and
And dual to a bridge disc
Dual to a bridge
In-
disc, that's right.
in the second
And
one.
what you were drawing, the one
So-
you just had didn't work. Yeah, don't try it again.
Yeah, so I'm just gonna go off script. This is probably the way to do it anyway, right? Pedagogically. Okay, I think as my first step, I do want to do this though. And the orange guy definitely becomes this, and the purple guy becomes this. And so now, yeah, the only difficulty here is now it's a little funny to get the both endpoints of the purple guy off of the orange one. I think that's why I had different bands in my notes. But let's just do it.
And so the orange guy is dual to that obvious disc, right?
The orange
Guy
guy.
is dual to that.
Yeah, that's right. That's my idea here, is to make the orange band so that it could be leveled into the bridge sphere and it's dual like this. Okay, so I think actually what I want to do is this. No, let's see. I want to do this. Where should this strand go? I guess it could kind of go like this. The truth. So all I've done is sort of pull that down, and I guess my purple band would sort of look like that now. Is that right?
That's dual to it.
Yeah. So this is not allowed by the definition of banded bridge position, because the endpoints of these bands should not project to the same bridge point. But this, I think, would actually. So
It works anyway.
it does work, yeah.
But if you didn't like it, you just do one more. I mean, if you just want to be inefficient about it,
Yeah, so
you
one
can
thing,
just do one more perturbation in between.
you could just do one more perturbation. I don't want to do that.
Yeah.
And you could check that, then you could unperturb, so you could undo it later. The other thing you could do is you can slide it. So maybe let's do that, because we haven't really seen that yet. So we can take this purple band and we can slide it across this guy. And so I always have to do this with my fingers, so it's sort of like right there. It's gonna walk here, and I think it's gonna untwist. So it could go to this.
Isn't that a swim?
It's not no, I'm not doing a swim. I'm just walking its endpoint over it. Like that. So again, sometimes it's easier to check on back. If this is the band I had, then it would sort of like go like this, walk across, and then undo. So it would have been that. I think that's right. This is a band slide. Yeah, and it gives us this condition which we wanted, which was that everything. So now we have sort of, this is the bridge disc for the purple band, and this is the bridge disc for the orange band.
So in practice, it's nice having bands kind of far away from each other
Yeah,
when you start out.
it is. Yeah. Yeah, or it's like in my notes, I started with a slightly different configuration here, and it made it a lot easier. Okay. So that's easy. And then the third step is to resolve B for B2, T2, I guess bar, because that's what it is, to get B3, T3 bar. Okay. So let's just look at what that looks like. Well, maybe I'll do it from here. So B2 looks like this. Okay, these bands. This. And then we resolve them to get So this is a little funny. Let's just draw it. Maybe you get that, which then fixed. Maybe this kind of funny. All right, and then the last step is, well, the last step is the claim that B1, T1, union B2, T2, union B3, T3 is the spine of the bridge trisection. In particular, if we sort of take the tangle projections of each one of these tangles, 2, 3, this is a triplane diagram. Okay, so what does that look like? 3 tangles. First one is this guy on top. Just like this. The second guy is this bottom one, but I need to remember to take the mirror. I get this. That. And the third guy is the result of resolving those bands. Again, mirrored. Okay. Now, so remember, what is a triplane diagram? Well, it's a triple of trivial tangles whose pairwise unions are unmixed. So we should be able to check that these pairwise unions are unmixed. So let's see. Let's draw them and see if it's obvious. I don't know how much work we want to do this, but if it's easy, we can do it. Okay. Well, let's cheat. This does look a lot like the L1 that we started with. I mean, in particular, it is L1, right? So unless we really messed something up, this should just be a perturbation of our original unlink. So I think that's still an unlink. This one, where does the unlinkiness of this one come from? So this is L2. The unlinkiness of L2, I erased my schematic, but L2 is the boundary of the sort of interesting piece of the trisection that came from the trace of bands. Okay, so if we screwed up our banded bridge splitting somehow, or didn't dualize our bands right, then this would, the problem could pop up here. But this one's, clearly unlinked also. And then, so this should be, then now that we should get L3 here. So let's see, 1, 2, 3, 4 under over 2. So here, this goes behind, this goes like that. And so this is L3, this is the caps. We haven't actually seen this link. This is what you get if you resolve both the bands. But actually, since it's a double, it should just be L1 again. The diagram should look a lot like L1. I guess probably mirrored. And after we've perturbed, I think I'm happy with that. Okay, good. Oh, and by the way, this also allows us to check the parameters, right? So this is a B equals 4 and C bar equals 2, 2, 2. So where we say C equals 2 when it's balanced. So yeah, we could just check that each component has each link has two components. And maybe we should, so that's the Euler characteristic. So we have the Euler characteristic is 3c minus b in this case, which is 2. So we should maybe expect that we're getting a sphere. We can also check connectedness and orientability. So we'll check orientability and in the process we'll get connectedness. So one way to check orientability is, and actually let's forget, but let's just sort of, let's go back to just thinking of this as a triplane diagram, because you don't really need to draw the mirrored components, the mirrored tangles below. That's just a sanity check. But for orientation, what we can do is we can start by orienting one of the bridge points. Okay? And this induces an orientation of each strand of that bridge point. So in particular, we'll have to orient the opposite endpoint of that red strand with a negative. But we get, so this is negative because that was negative, which means this is positive, which means this is positive, which means this is negative, which is that negative. So those are like sort of all of the orientations that came from one of the components of red. But we get the same guys over here. And these percolate to give us more, right? These give us plus and minus. So that means this is minus and plus, which means this is minus. And if that's minus, then that's plus. So then we completely filled in our Sudoku. And that's a proof of connectedness, because starting at one base point and following this, the spine itself is a connected graph. Okay. And this will be an orientation on the surface if everything's consistent for each tangle. So for example, minus plus, 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 minus plus. So this is an oriented, connected, closed surface with Euler characteristic 2. So it's a sphere, which I guess we know. But that's how you do things like that. All right. Okay, I'm going to cheat ahead a little bit, and because something this kind of interested me when I was. See, this one's a little bit different. Yeah, in my notes, this came out a little bit differently, and it looks. The diagram that I got in my notes, which you can see online, but it looks a lot like the diagram. I gave the diagram, I think, for the spun trefoil. And the last class, I didn't. Okay. So let's just get another example then.
You did not in arguments.
Oh, okay. So the spun trefoil. So yeah, I mean, I guess an exercise at this point is for any banded links that I've given you, or any that you know of, can think of that I haven't given you, come up with a bridge trisection. So in particular, I'm pretty sure I've given you a banded link diagram for the spun trefoil, and so you can verify that this is a triplane diagram. And then so the question I'll just pose is, triplane diagrams for the spun trefoil and the stevedore double look very similar. Which is not a question, but I can put an ellipse and a question mark, and that's a question. So this just kind of popped out at me, and I don't know exactly what's going on here. So anyway, something to think about. Maybe there's some silly answer to that question, but maybe I did something wrong.
The trefoil connects on its mirror. Is that the stevedore?
No, it's a square knot.
It's a square knot.
Yeah, otherwise they would be the exact same. Yeah, exactly. So yeah, this is the double for the ribbon disc for the square knot, the trefoil connects on the mirror, and this is the double for the ribbon disc for the stevedore. So they're both ribbon, they're both pretty nice. Maybe I'm missing something, but might be something interesting to investigate. Okay, well, we're basically out of time, so let's see. What should we do? Maybe, what can we do on the fly? Oh, well, I guess let's do our V2. Well, so, I mean, one example I gave last time, which is, very easy. So here's a banded link, L1B, just an unknot with no bands. There's a cup and a cap. In fact, let's do something a little bit more exciting. Let's do an unlink of, say, C components. Well, this is pretty easy to get in banded bridge position, and we get a very simple bridge trisection and triplane diagram. In particular, all three tangles are exactly the same. And so let's unlink C two spheres admits C bridge trisection. Okay, that's comfortable. So let's do a more interesting example, which is this guy we've had before. I wonder if I could possibly get the crossing right. So this is a picture of one of the unknotted RP2s. And check which one it is, I suppose. And again, this I've sort of perhaps accidentally made very easily bridge banded, get banded bridge splitting. So just to check this band is here. And so we take the top tangle as our red tangle. We take the bottom tangle as our second as our blue tangle, and our third tangle is the result of resolving this band, which looks like that. So when you resolve this cap kind of comes over here, and you get a little cap right there. And so this I showed you the other day, probably without proof that it's RP2, but in fact we see that the unknotted RP2s admit. Now, what type of a bridge trisection is this? Oh man. Well, the fact is that all three of the pairwise links are unknots. The cup is an unknot, the cap is an unknot. So I guess what's interesting is that red, blue, green, which is what's coming from the bands, is also unknot. And just remember that complexity, C2, comes from B minus N. So here the bridge number was 2 and the number of bands was 1, so that's why that 1's coming. Here the bridge number was 4 and the number of bands was 2. So maybe next time I'll talk about handle triangles. Anyway, this type of bridge triangle. So as an exercise, you can check that you can't orient it. And maybe another good exercise is to come up with bridge trisections for all the unknotted surfaces. And maybe come up with different ones. Yeah, so I think there's a project sitting behind understanding all the different bridge trisections for unknotted surfaces. Something like that. Okay. How do we count?
Are CC bridge trisections possible?
Yeah. These are them.
So additional needs.
Yeah, that is. Yeah, one thing I think we will do next time is classify some bridge trisections. Yeah, so another exercise would be to prove that a CC bridge trisection is, it would be to prove that it's an unlink of C2 spheres.
Another good project in light of Adam's stuff is to classify planar C, B, C1, C2, C3 bridge trisections.
The crossingless ones.
Yeah, crossing.
Yeah.
ones, yeah.
Crossing.
Which can also be thought of just ones that actually are surfaces in R3.
Yeah. So probably starting now, we should start systematically recording these projects. Okay. No class Monday? No.
So you actually trisect the